Now we'll discuss different applications of calculation of gravitational field strength, and here the first is gravitational field strength due to a uniform rod. And we are going to discuss two cases in this. Case 1 for this situation is at an axial point of rod. When we talk about a uniform rod, we can state if we are given with a uniform rod of length L and it is of mass M, then the line on which the rod is placed is called axis of rod. And on the axis of rod, if there exists a point P located at a distance R from the near end of the rod, and we are required to find the gravitational field strength due to this rod at point P. And obviously, as the rod is an extended body, we cannot directly calculate it. We'll consider a small element at a distance x from the point P and say it is of width dx. We find out its mass. The mass of this element can directly be given as m by L dx, as for the mass m, the uniform mass m, the length is L in which it is distributed. So for the element of length dx, it will be m by L dx. So in this situation, due to this elemental mass dm, say gravitational field at this point is dg. Here we can write gravitational field strength at P due to dm is, say it is dg, then dg can be directly written as we are having the relation of gravitational field due to point mass. It is g dm by x square as magnitude. If we substitute the value of mass, it will be g m by lx square dx. So we can simply calculate the net gravitational field at point P due to the whole rod. It will be integration of dg, which is integration of gm by lx square dx, and we'll apply the limits of integration on x from r to r plus l. So this will give us Gp is equals to Gm by L. 1 by x square, when integrated, it will be minus 1 by x. We apply the limits from R to R plus L. So here the result we are getting is Gp is equals to Gm by L. After substitution of limits, we are getting is 1 by R minus 1 by R plus L. This is a standard result for gravitational field strength due to a rod at any of the axial point which is located at a distance r from the near end of the rod. So just keep the result on your tips. And now we'll take up another case in which we talk about gravitational field due to a uniform rod on its equatorial point. Let us discuss the second case of calculation of gravitational field strength due to a uniform rod at an equatorial point of rod. So if we are given with a uniform rod which is of mass m and say its length is L, and in this situation the perpendicular bisector of the rod is termed as equator of rod, and for the uniform rod, say there exists a point P which is located at a distance r from the midpoint O of the rod, and we are required to find the gravitational field at point P. Then the process is same. At a distance x from point O, we consider an element of width dx. The mass of this element dm can be written as m by L dx, and due to this element, if we just have a look on gravitational field at P, this gravitational field dg will exist in a direction directed towards dm. As always, remember, a gravitational field at any point due to a point mass is always directed toward the point mass. So in this situation here, we can write if dg is gravitational field strength at P due to dm, then in this situation we can simply write the value of dg to be equals to g dm by the distance square. When we talk about this distance, as this is x, this is r, this distance can be written as root of r square plus x square. So it can be written as r square plus x square. If we square it, radical sign will be off here. So if this dg, so for the whole rod, if we wish to integrate it, we can see the direction of dg will change as the elemental mass dm is moving from one end of rod to other end. So here it is better to go for the components of this elemental gravitational field. One is in direction directed towards rod perpendicular to it, which will be dg cos theta, and other is parallel to the rod, which is dg sin theta. So here you can see the gravitational field due to the elemental mass we have resolved into mutually perpendicular direction, which can be taken as x or y axis or along the rod and perpendicular to the rod. So in this situation, when we integrate the element from this end to this end of the rod, corresponding to each element on the right half of the rod, there exists an element on the left half, due to which the elemental gravitational field will exist in this direction, which is having a parallel component opposite to this dg sin theta and will always balance. So we can state the gravitational field due to the rod will exist only in vertical direction, as all horizontal components of these elemental gravitational field will cancel each other. So here we can say net gravitational field at point P is, in this situation, net gravitational field Gp we can write as integration of dg cos theta. So in this situation, if it is dg cos theta as dg sin theta, we have discussed that will cancel each other corresponding to all the elements on left and right half of the rod, whereas dg cos theta will all be added up. So if we substitute the values, we can see the value of Gp we are getting is integration of dg. If we write this g dm, we can write as m by l r square plus x square into dx multiplied by, in this triangle we can also substitute the value of cos theta as r by root of r square plus x square. So it is r by root of r square plus x square. And the x will be integrated from left end to the right end of the rod. So here limits of integration will put as minus L by 2 to plus L by 2. So in this situation, this Gp we can write, the constants we can take out as Gmr by L. Integration from minus L by 2 to plus L by 2, it is dx by r square plus x square to power 3 by 2. Let's continue the integration on the next sheet. Now to integrate the expression, we can substitute let x is equals to r tan theta, and if we substitute x equals to r tan theta on differentiation of x, we get x dx is r sec square theta d theta. If we substitute the values here, you can see finally we are getting gmr by l. This integration of dx we can write as r sec square theta d theta divided by, the denominator will be r square tan square theta plus r square, that is r square 1 plus tan square theta can be written as r square sec square theta. So it will become, I just solve it here, you can see it is r square tan square theta plus r square to power 3 by 2. If I just substitute the value of x here, so this will be r square sec square theta to power 3 by 2. Here this 2 gets cancelled out and we are getting it r cube sec cube theta. So if we substitute it here, it will be r cube sec cube theta, where this cube and this square will cancel, this r square and cube will cancel. So final result here we are getting is gm by lr integration of cos theta d theta. If we integrate cos theta, we get it sin theta. So it is gm by lr and this is sin theta. If it is a time to substitute limits, so first we need to resubstitute the value of sin theta in terms of x, as minus L by 2 to plus L by 2 are the limits of x we are having. So this will be gm by lr Here as tan theta is x by r, sin theta can be written as x by root of x square plus r square from minus L by 2 to plus L by 2. If we substitute the limits, this will be gm by lr, and on substituting limits we'll be getting x as L by 2 divided by root of L square by 4 plus r square. And if you substitute the lower limit, it is negative of the same value, so we can multiply it by 2. So in this situation, this 2 gets cancelled out, and on solving we get the gravitational field at point P will be 2 gm by r root of L square plus 4r square. That's the final result of gravitational field due to a uniform rod at an equatorial point located at a distance r from the center of the rod.